So for number one, we want to analyze the logical form of each of these following statements and just construct the outline of a proof. So we don't actually have to prove this, we just have to show the outline of how a direct proof goes. So all we have to remember is that a direct proof, we're trying to prove a conditional statement, right? So we are attempting to prove the statement if P then Q. And so the way that we do direct proofs is that we assume that P is true, and then we show that Q must necessarily follow. So assume P, show that Q necessarily follows. Okay, so once we have this, let's begin. So for A, they want us to outline a proof that if G comma star is a cyclic group, then it is abelian. So what we begin by doing is we assume the hypothesis, and the hypothesis is this one: if G comma star is a cyclic group. So we begin by assume that G comma star is a cyclic proof. Not cyclic proof, cyclic group. Cyclic group. And then we would develop our proof, and we would show that the consequent, which would be this one, is abelian, necessarily follows. Then we would have to show then G comma star is an abelian. Therefore, so our proof goes that if G comma star is a cyclic group, then it is abelian. Okay, and that is the outline for the direct proof of A. Now let's do the direct proof of B. So for B, we're attempting to show that if, what's our hypothesis? If B is a non-singular matrix, then the conclusion that the determinant of B is non-zero, then that follows. And actually I should just color code this. Then the determinant of B is non-zero, then it follows. So we're going to do the same. We're going to assume that that B, bold B, is a non-singular matrix. And then we would develop our proof, and we would show that the conclusion necessarily follows. So we would have to show then the determinant of B is non-zero. And so our conclusion is, so we say, therefore, if B is a non-singular matrix, then its determinant is non-zero. So that is it for the direct proof of B. So all we've done here is we've assumed the antecedent, shown that the consequent follows, and so proved the conditional. So once we've done that, let's now proceed to item C. So I'm going to erase all of this. And let's see, item C, what are we assuming? Well, we're assuming two things. We're assuming that A, B, and C are sets, and we're assuming that A is a subset of B and B is a subset of C. So that's our hypothesis, right? Our hypothesis is that A, B, and C are sets, and that A is a subset of B and B is a subset of C. So what we're going to do here is say, suppose A, B, and C are sets, and then it's telling us to assume, rather it's not telling us, but we're going to assume P and show that Q follows. Actually, now Q is A is a subset of C. So assume that A is a subset of B, so A is a subset of B, and B is a subset of C. So once we have assumed this, then we would work our proof, and actually I should put the item here, and then show the conclusion, which is therefore, actually I'm going to say then A is a subset of C. So we have assumed the hypothesis and shown that the conclusion necessarily follows. So we say, therefore, if A is a subset of B and B is a subset of C, then A is a subset of C. And maybe I should put this so that we don't confuse the subset notation with C. Okay, so that was it for item C. Now let's do item D. So once more, we're assuming the hypothesis. What's the hypothesis? It says outline a direct proof that if, so the hypothesis is the maximum value of the differentiable function f on closed interval AB occurs at x naught. So that's quite a long hypothesis, but that's our hypothesis. That's what we're assuming. And we want to show that either x naught is equal to A, x naught is equal to B, or f prime of x naught is equal to 0. So what we're going to do here is we're going to say, okay, assume the hypothesis, right? Assume that the max value of a differentiable function let's see, f on closed interval A, B, assume that occurs at x naught. So once we have assumed this, then we would have to develop our proof, and we would have to show the conclusion, right? Then our conclusion is marked in blue. Then either x naught is equal to A. Actually, I should put x naught is equal to A, or x naught is equal to B, or f prime of x naught is equal to 0. Okay, so we assumed the hypothesis and then shown that the conclusion necessarily follows, right? And then you would say, therefore, if the maximum value of a differentiable function f on closed interval AB occurs at x naught, then either x naught is equal to A, x naught is equal to B, or f prime of x naught is equal to 0. So I'm not going to write that down because it's going to be too long. And lastly, let's do item E. So I'm going to erase all of this. Lastly, we're going to do item E, which is item E. So what's our hypothesis? Outline a direct proof that if A is a diagonal matrix, so that's our hypothesis. Actually, I've color-coded this wrong. Our hypothesis is in yellow. then the conclusion is that A is invertible whenever its diagonal entries are non-zero. So once more, we're assuming the hypothesis and showing that the conclusion necessarily follows. So we're going assume that A is a diagonal matrix. Then we would develop all our arguments, and we would show that the conclusion necessarily follows. So we would show then A is invertible. My handwriting is quite terrible. A is invertible whenever I should have put all. Whenever all its diagonal entries are non-zero. Okay, so we've assumed P, shown that Q necessarily follows, and so our conclusion would be, therefore, if A is a diagonal matrix, then A is invertible whenever all its diagonal entries are non-zero. Then A is invertible whenever all its diagonal entries are non-zero. Okay, and that is it for item E. So all we've done here is we've outlined a direct proof which assumes P and then shows that Q necessarily follows for these 5 items here.